Alright, so vectors, a reminder of some stuff that we had before. So some definitions, so vector quantity has a size and a direction. Notation of vectors, so if we've got something vector from A to B, goes from A to B, you know that direction by the arrow. It's written AB with an arrow over the top. There are other ways of doing it sometimes. I'll get to the other ways of doing it later. But if we're doing AB, then it would be written in that form there if we're using the two endpoints. So it says here sometimes it's represented by a single letter, so we might say that this is, I've used B there, so I might call that AB, I might call it, V or something like that. So sometimes you might see a little squiggle underneath, but on exams quite commonly you'll see it just as bold. This is the vector. Alright, so a column vector is what it's called. It's represented in kind of a column matrix. Alright, 3, 2, so the 3 would be in the x direction and the 2 in the y direction, when we get to it, ij and then k. Alright, so from where our starting point is, we go 3 to the right, 2 up. Then the magnitude of the vector, or the size, how big it is, how long it is. So it's length, written magnitude, absolute value signs, so length from A to B. And so if A to B is represented as a column vector, we got the x direction, the y direction, then the magnitude of it we just get by square root of x squared plus y squared, which of course is just, oops, gone the wrong way, which of course is, we want to find the length of that there, using that and that, it's just Pythagoras, isn't it? Okay, so we've done that last year, yep. Alright, so addition of vectors, so if we're going to add vectors geometrically means drawing a diagram, then if we're going u plus v, then as it says here, we place head to tail. So we go u plus v, so we place the tail of v on the head of u. So here's a couple of examples. So there's u plus v, and then the result goes from where we started to where we finished, and so u plus v is that one. Now, if we have it in column vector form, u and v, we've already got the x's and the y bits. It's just simply a matter of just adding those two things together. So 4 plus negative 1 is 3, 1 plus 3 is 4. When we add those, if we do it in column vector form, or if we do it geometrically, we do like that. Alright. Anything you haven't heard of before so far? No? No. Alright, next. Scalar multiplication. So scalar just means a number. So as it says there, it changes the length. And so 2u would be twice the length of u. And the other thing we need to point out is if it's multiplied by a negative, then the direction gets reversed. So if u is this way, like so, then 2u would be like that, and negative 2u would be like that. these would be parallel, even though mine don't look at. Alright, now subtraction. If we're doing subtraction geometrically, then what we need to do is we need to write the sum in terms of addition. So we would change u minus v, and we would change it to adding negative v. Alright, so that's for geometrically, that's the easiest way for us to do things. And so then, if we're adding, we do head to tail, and the tail's the negative v. And of course, as I mentioned before, negative v is the opposite direction. So here's a little diagram here, u and v, and so negative v's the opposite direction, and so then we're adding, so we put the head of u to the tail of negative v, and there is u minus v. All right. Next thing that we need to go over is so here we've got some information. It says the vector u is defined as the line, not time, line, the line joining 2, 6 to 3, 1. And so vector u is written in this column vector form. We need to find the a and the b. So the diagram that I've got here, so I've got the point 2, 6, and then the point 3, 1, and the vector u is this vector goes there like so. So we need to create ourselves a right angled triangle like so, so that we can, of course, a is how much we move in the x direction and b is how much we move in the y direction. So in the x direction we're going from 2 to 3, so we're going across 1. And from the y direction we're going 6 down to 1, because we're going from 6 down to 1, we're taking 5. So that there we get take 5. Alright, anything about that so far? Any coming back to you? Yep. Alright, so this example here is if we're illustrating, say, a vector sum, we might be given some vectors, AB plus BC plus CD. And these things are in common. So even if it was written not in that order, you would rearrange it so that, say for example, I had AB plus CD plus BC. You would rearrange it so that you're going from A to B, so you would rearrange that so that the next one where you're starting where you finish. Which kind of makes sense. So here's a diagram, so AB goes there, and then if BC points this way, joins up, and then CD brings us down to there. So when we've actually added all those together, we then, as we did, I mentioned before, we go from where we start to where we finish. And so the sum of all of those goes directly from A to D, which you can also pick up straight away. What would it be? Because you've got your A and your D there, so after you've started at A, where do you end up? You end up at D. Alright, anything about that one? Alright, parallel vectors. If vectors are parallel, then they got to point in the same direction. Or the opposite direction. Alright, so I've got some vectors, for example. I'll just draw some. It's vector A, this one, vector B. They're parallel, but I could also have a vector C that would also be parallel. Even though it's pointing the opposite direction, it's still, the directions are parallel. Alright, so it can be the same direction, or it can be 180 degrees the opposite direction. And so, if it's a geometric, you can look at it and you can see. But otherwise, you can have a look at something like this. So, as it says here, if U and V are parallel, then U is some constant times whatever V is. So, here's an example. We've got U here is the vector 2, 3, and V is the vector -6, -9. And we'll notice that -6 and -9, -3 goes into both of those, so we can take that out. And when we do, -3 times 2 gives us the -6, and -3 times 3 gives us the -9. And so now what we've got, so basically we've got vector U there. So this vector V that I've got is actually -3 times vector U. So therefore, it's parallel, it's pointing the opposite direction, and it's 3 times this long, but it's parallel. Alright, another thing that we look at is what's known as position vectors. So position vectors locate a point in space relative to the origin. Alright, so in this case here I've got point A. Point A is up here. There's point A. And so the position vector describing that would go from the origin, so O, through there to A. So OA is that position vector. We always use O with a position vector, O for origin. So it goes from the origin to wherever that point might be. Alright, and we'll get to using position vectors. So the previous vectors that I've talked about haven't been position vectors, so they haven't been identifying a position in space. They've just been vectors that are a certain length pointing in a certain direction. Where they actually are could be anywhere, but these position vectors, because the origin is a known point, then these position vectors are in specific places. Right. Now, if we have, I've just talked about 2 dimensions, but if we have 3 dimensions, vectors in 3 dimensions, they're just like that, and so that's X, Y, and Z. Or when we get up to it in a minute, I, J, and K. Alright, but then we do the same things with those as we do if we just had 2. Alright, let's have a look at a couple of examples. Alright, so let's have a look at what we can do. For the cuboid shown, alright, so cuboid's a box. Like so, it's a mathematical name. This particular cuboid, we've got this vertex down back here is called vertex O. This one is A. This one is B. This one is C. And we're going D, E, F, and G. All right. So, in terms of vectors, we're going to let vector A equal OA. We're going to let vector G equal OG. And we're going to let vector C be OC. Alright, so vector A is this line here. Vector G is this one here. And vector C is this one here. And so what you can do is we can use those and find the following. In terms of A, G and C. So the first one is O to B. Second one is G to D. And the third one we're going to look at is F to A. All right. So, A to B, I'm going from here to here. There's a variety of different ways that we could get there. One of them is that we could go to A first and then to B. So A to B would be the same as O to A plus A to B. All right, now O to A, we've already been told that vector A is that. Now we've got to think about A to B. So A to B is this edge here. Now because this is a cuboid, what can you tell me about this edge and this edge? They're parallel, aren't they? So A to B is pointing in the same direction as O to C. And so what we can do say then is because A to B is parallel to O to C, what we can then do is we can replace this A to B by the O to C, and the O to C is vector C. And so in terms of A, G and C, O to B is the same as A plus C. And G to D, when we look at G to D, it's just a straight line that just bang goes straight there. And G to D, of course, is parallel to O to A. And so if it's parallel to O to A, then we can just say that that's vector A. All right, next one, F to A. All right, so we go from F and we end up at A. So there's a variety of different ways that we can get there. How will I go? Let's go down there and around that way. So I'll go F to C to B to A. Yeah. There's other ways you could get there. Oops, F to C, and from C to B, and then from B to A. And so now we need to have a look about things. All right, F to C, that's this one here, which is parallel to that side. And G is when we go from O to G, but we're going the opposite way, aren't we? We're not going up, we're going down. So because we're going the opposite way than O to G, we need to put in a negative. And O to G, of course, is G. All right, then we're going from C to B, and that's parallel to OA, which is A, plus A. And then we're going V to A, so we're going this way, which is parallel to OC, but the opposite direction. So I've got ahead of myself when I put a plus there, opposite direction to C. And so there it is. And it wouldn't matter which, I went round that way, but it wouldn't matter how you actually went around, because this thing's a cuboid. All of these edges are all parallel, all of these edges are all parallel, all of these edges are all parallel. So whatever pathway you went, you would still end up with that. All right, now I haven't given you notes about this one. Perhaps I should have, but I didn't. So this next one you'll have to write down, and that's linear dependence.
You've given it to us.
I have given it to you, have I?
Yeah.
Oh, must have changed my mind then. I tossed up whether I would or wouldn't. In the end. All right, so linear dependence. So as it says here, linearly dependent if they're parallel. Otherwise they're independent. So that means vector A, it would be k times vector B. All right, and k can't be equal 0. So they'd be linearly dependent, and which is all very nice. But if we have 3 vectors, so 2 vectors, they're linearly dependent, they're parallel. 3 vectors, though, they fit into this equation. So vector C would be some multiple of vector A plus some multiple of vector B. Right, so if you can take some vector A and vector B and multiply them in some way, then add them together to get C, then they're linearly dependent. And M and N are some numbers, and it's, as it says there, they can't both be 0. All right, so let's have a look at an example. Then. All right. Right, so here's a couple of examples where we've got, first example, part A, we've got two-dimensional vectors, and part B, we've got three-dimensional. All right, so let's have a look. Those solutions. So for part A, so remember, if they are linearly dependent, then our vector C we can get by taking some multiple of that plus some multiple of this. Will give us this. So how do we go about it? All right, we go about it by putting the vectors in. So this is 5 and 6. And that's m times A, which is 2 and 1, plus n times B, which is 3 and negative 1. And so now, simply all we do, remember these are constants, so we would just multiply those in. So these are written in n, not m, like so. So these are written in matrix form. And so when we're adding, excuse me, we just add the corresponding elements together. So from that we know that 2m plus 3n has got to be 5, and 6 has got to be m minus n. And then we solve simultaneously. And because I've prepared one earlier, you find in this case that m would be 23 on 5 and n comes out as negative 7 on 5. Alright, both of those are just numbers. So some multiple of A plus some multiple of B, and these are the multiples, give us C. So in this case, they are linearly dependent. Alright, so if we tried to solve this and we couldn't solve it, we've got no, then they wouldn't be. But because we can solve this and we can find a value for m and n, they're linearly dependent. Alright, so let's have a look and see what the other one tells us. And here's the other one. So B, we're looking at B, then C has got to be equal to, whoops, and let's just put C in, which is negative 1, 0 and 1. It's got to be m times A, which is 3, 4, negative 1, plus n times 2, 1 and 3. So this time, we'll get 3 equations. So negative 1 is got to equal 3m plus 2n. And we'll go that first row. The second row, 0, is got to equal 4m plus n. And then our third row, 1, is got to equal negative m plus 3n. So we've got 3 equations, 2 unknowns, so we can solve them pretty easily. And because I've prepared one earlier, if you solve these 2 simultaneously, you get that m is 1/5 and n equals negative 4/5. All right. Now, we have a third equation here in this one because we've got x, y and z, or I, j and k. And so it's all very well for us to find these values for m and n using these two, but they've also got to fit in with this as well. So we need to check to make sure that those two values we're going to check that these numbers work for the third equation. So that would say that 1 should equal negative m, so negative 1/5, plus 3 times negative 4/5, which would be negative 1/5 minus 12/5, which is negative 13/5, which is not equal to 1, is it? Alright, so even though we've managed to find some values of m and n using these two, those values don't work for this one. So it's not linearly dependent, which we would write as linearly independent. Right. Anything about that before we move on to the next bit? No? Right, so again, there's some definition stuff that got the notes there for you, so that we don't spend time writing all that out. All right, components of a vector, bits of a vector, we can split vectors up. It's not quite the best title, but anyway, not to worry, we'll survive. So, a unit vector. We use unit vectors quite a bit. And a unit vector is a vector of magnitude 1. Alright, so unit means 1 unit, so its magnitude is 1. And the way we write a unit vector is we put a little hat on it. So A with the hat means the unit vector. And so what do we know about A hat, or unit vector A, is it's the same, points in the same direction as vector A. But it has a magnitude of 1. Now, vector A might not necessarily have a magnitude of 1, but it's quite simple to determine what vector A hat is from vector A, because all you need to know is how long vector A is, and if you divide vector A by how long it is, that gives you the unit vector A hat. So A hat is simply vector A divided by the magnitude of vector A. Alright, and so what we're going to do is we're going to use these unit vectors if we want to know about directions of certain things. We use a unit vector to say which direction something's pointing. Alright, so let's have a look then. Cartesian form of vectors. So when we go to Cartesian form, rather than using necessarily a hat, which we might be able to use, but we've got x, y and z axes, so I've already kind of mentioned this. So a unit vector in the positive direction of the x-axis, that's vector I. Alright, so if we got our, I've got better diagrams below. So if we've got something that's pointing in the x direction, we use I to indicate that it's pointing in the x direction. For the y direction we use J, and for the z direction we use K. Alright, so 2 dimensions first up. There we go now, 2 dimensions. So 2 dimensions, just the x and y directions. So we've got this point here, up here. There it is there, that point. And so the position vector is that one there. And so of course it has a component in the x direction and then a component in the y direction. So when we're writing this particular vector, it will be so much I plus so much j. And so as it says here, xi plus xj gives us that vector. And so O to P, xi plus yj. Now find the distance there, this r if you like, because we just use our old friend Mr. Pythagoras as usual, x squared plus y squared square root of. And for the direction that it's pointing, we always use the positive x-axis. So that's this, and we go in the anti-clockwise direction. Theta, of course, theta is related to the lengths of those sides, opposite over adjacent. So tan theta is y on x. And so that then, excuse me, helps us figure out what the polar form of the vector is if we need to use the polar form. Anything so far? You remember this stuff from last year? Yep, good. I'm banking on you remembering something. All right, then of course we can go into 3 dimensions. And so 3 dimensions, difficult on a 2-dimensional bit of paper there. So y and z are on the screen and x is pointing out. Right, that's what it's supposed to be. So point P's here somewhere, out here somewhere. Point P. Out here somewhere. Alright, so again, of course, we could come across a bit in the Y, we've got to come up a bit, we've got to come out a bit. Got this little dotted cubey thing there, it's supposed to represent. Does that make any sense at all? Does make sense? Good. Alright, so this time OP, of course, it will have a component in the I direction, component in the j direction, a component in the k direction. To find its magnitude, it's just an extension of Pythagoras. I could work through it and you work through it. You use Pythagoras twice to get this. But R is just x squared plus y squared plus z squared. That will tell you how long that vector is, the one sticking out there. And the direction it makes with a particular axis. So this is where it's a little bit different than the 2-dimensional one. The 2-dimensional one we're always referring to the x-axis, but with the 3-dimensional one we look at the directions it makes with any particular axis. So with the x-axis, it's cos of alpha. So we're using cos because what we're doing is we're using the x-axis and we're using that there. So if we're looking at this in here, there's our alpha, and here's the x-axis, and we're looking at this angle it's making with the x-axis. I need that component. The length of the vector is the other thing we can work out, and of course that's adjacent, so it's cos. So whether that's the x-axis, whether it's the y-axis, or whether it's the z-axis, it's always the adjacent and the length of the vector, which of course is cos. Alright, and the length of the vector bit stays the same, A to P, which of course is R. It's just how much it goes in the X, the Y or the Z direction that might change. Alright, anything about that one? Alright, let's do some examples. Okay.
Is that a Tuesday for the first part?
2, yep. Alright, so let's have a look. Part A says vector A minus 2 lots of vector B. So we can write it like this. There's vector A minus 2 lots of vector B, or you could put them in columns if you like, whatever, doesn't matter. Minus 2 lots of vector B, which is 3i, I forgot my minus 2, that's a 2 as well. 2k. Alright, so we've got I. Let me just expand that bracket first. Probably be able to do this stuff in your head, but anyway. So minus 6i, minus 2 times 2 minus 2 is plus 4k. And so now you just put together your bits. So you've got an I there and you're taking 6 i's, so you've got minus 5 i's. It's only one lot of j's, that's that one. And you've got minus 1k there, plus 4 is plus 3. Alright. Then B, we're asked for the magnitude of vector A. And so that's the square root of all the magnitudes. All the magnitudes of these squared, so 1 squared plus 2 squared plus negative 1 squared. And then stick all that together. So you get 1 plus 4 plus 1, just square root 6. Okay. So look at what else might we do. Alright, this one's a little bit involved. Let's do this one. All right, so when I'm doing this, what I like to do is I like to draw a bit of a diagram. So these are just points, excuse me, on the Cartesian plane, if you like. And the origin is O, and we want to know what the vector A to B is. So what I like to do is just draw a rough sketch here so that we can get a bit of an idea of what's where. So, point A is at 2 and negative 3. So there's point A there. And then point B is 1 and 4. So there's B there, which is 1 and 4. All right. Now, the question in part A says that we want vector A to B. So we want that. So to get that, what we can do is this. Excuse me. Is, because they've told us that the origin is here at O in the middle here, then we can use that to help us in the following way. So from A to B, because these two coordinates, of course, are relative to our origin. So if we work back to the origin, we can say, okay, well, we can go to there, and then we can go to there. So, and then that gives us the A to B. Yes? So A to B is A to O plus O to B. Now, these points here, 2, negative 3, that's not going from A to O, that's actually from O to get to there. So that's the negative of O to A. All right, which way there. Because if you recognise this pattern, if you are using the origin and the position vectors, if you're going from A to B, then the pattern's always this, it's always OB minus OA. So if you were going from F to G, it'll be OG minus OF. Alright, so it's always the position vector relating to the second thing minus the position vector relating to that first thing. Alright, so O to B then, well, O to B of course is related to that. And so that's I plus 4j. And vector OA is related to that, which is 2I minus 3j. So now we put those in and we add them together. So, where are we? So, I plus 4j minus 2I minus 3j, which would be minus I plus 7j. All right. The next part. Part B says the midpoint. All right, the midpoint. What do we know about midpoints? Obviously they are in the middle. So here's my midpoint, M. And so they are in the middle. So, the midpoint of AB. So what are we trying to find out? We're trying to find out where that is. So we're trying to find that there, aren't we? That position vector. Because that would then locate where it is. Now that position vector, if I'm going to go, so what I'm, in the end, midpoint, what I'm after is OM, because that will then tell us what those coordinates there are. So how can I get from O to M? Well, there's a couple of different ways I can go. I'm going to go from here to here. I'm going from O to A, and then I'm going from A to M. Yes? Happy with that? Alright. So B. I want O to M, and I'm going from O to A, and then I'm going from A to M. Now, what do I know about A to M in terms of A to B? Anything? M is the middle. So the distance there to there is half of there to there, yeah? This vector, A to M, and this vector, A to B, starts with P. Parallel, thank you. They are parallel. And what did we say about two vectors that are parallel earlier on? That they're related to each other in what way? Some constant times, yes? And this constant would be midpoint, halfway, is it not?
Yeah.
So the constant would be a half. So from that we know that AM is a half of AB. So, and that's handy because we already know AB. We've figured that out over here. So O to M is O to A plus a half of A to B. So O to A, we know that, 2I minus 3J. And then plus a half of A to B, and we figured out A to B over here. Whoops, negative I plus 7J. And so then we go 3 over 2I, a half. Yes, a half. Plus a half J. 7 over 2. All right. Now, didn't ask us for this vector, position vector, did it? It asked us for the midpoint, so the coordinates, the x and the y. Now, the coordinates we get from the midpoint, from the position vector, because the I is in the x direction and the j is in the y direction. So point M has coordinates 3 over 2 and 1/2. All right, one more example. Told you that today was going to be a long one. All right, last example. Where are we? So we've got a three-dimensional vector, and I want to find two things. I want to find its magnitude, and I want to find the angle that it makes with the y-axis. All right, so the magnitude of A is what we would call R, and to get that, it's the square root of all the individual ijk components squared. 1 squared plus 4 squared plus negative 3 squared. Which is the square root of 1 plus 16 plus 9, which is the square root of 26. All right. Part B, the angle it makes with the y-axis. So in the notes previously I called that beta. And so cos of beta is related to what? What's it related to? It's related to the bit in the y direction, which is over the magnitude of the vector. And the bit in the y direction, up here is 4. And the magnitude of the vector is just found to be 26. Root of is 26, I should say. So our beta would be cos minus 1 of 4 over root 26. Which you'd then get your calculator out. Probably be more information about how they want you to express that angle. But it's approximately 38.33 degrees, which is 38 degrees and 20 minutes. Yes, no, maybe?
What's that last bit?
Degrees and minutes? Don't you know degrees and minutes? Who's been teaching you maths all these years? So if you want to break a circle up into, or a whole, you want to break a degree, instead of breaking a degree up into decimal bits, if you break a degree into 60 minutes, into 60 bits. So to find the 20 minutes, you go 0.33 times 60. That's 20 minutes. Back in the ancient times, degrees, minutes and seconds, I thought that using dividing it into bits of 60 was a good idea.
Is that something you need to know?
Is it something you need to know? Yes and no. Because your calculator can convert. So, your calculator can convert. So, where's our calculator? Come on. So, in our calculator, in our main transformation, DMS, to DMS, 38.33. Degrees, 19 minutes and 48 seconds. So I've rounded it to the closest. So that's action, transformation, DMS, to DMS.
Yeah. I don't think I've ever been taught that. The internet.
In year 10, didn't we do that in year 10?
Not that I remember.
All right, that's it.